All right, welcome to another discussion of our WebAssign homework. In this case, we're in section 7.2. We're looking at partial fractions with quadratic factors. So quadratic meaning degree 2. We're going to have degree 2 polynomials in the denominator that cannot be reduced further. Most of these are going to be in the form of x squared plus a squared. You need complex numbers to factor those. Actually, right on cue, here is a factor in the form x squared plus a number, plus a positive number. There's no way to factor x squared plus 3 without invoking square root 3i and square root minus square root 3i, which is, yeah, those are complex numbers, and we're not going to worry about that for a class that works with real valued functions. So here we are, right? Because the x squared plus 3 cannot be broken down any further, and yet in our partial fraction decomposition, we need our numerator to be of lesser degree. It is hasty to assume that, as has been done in this decomposition, that the numerator would necessarily be of degree 0, a constant. A degree 2 polynomial downstairs could have a degree 1 polynomial above and still be a partial fraction, still have a numerator of lesser degree than the denominator. So the x is fine as a over x. There's just one copy of that. But the x squared plus 3, that irreducible degree 2 factor, needs a bx plus c above it. That's just a part of the form of a partial fraction decomposition that sort of needs to be known, and what this enforces. So ultimately this is false because we would need a bx plus c in the numerator. What about for 2? Oh my goodness gracious me. Fortunately, my gosh. All we have to do is write out the form. Oh man, this was going to look really heinous. I'm going to guess, and it's true, that this x to the fourth plus 18x squared plus 81, that will factor. That will factor as x squared plus 9 quantity squared. Note, the x squared minus x also factors as x times x minus 1. So the form, fortunately, we don't have to solve for the coefficients, just to write out the form. So looking at the x squared minus x, there's a factor of x there, so we're going to need an a over x factor. X minus 1 is the second factor there. You're going to need a b over x minus 1 factor. And now for the expression x squared plus 9 quantity squared, each of those x squared plus 9s are irreducible degree 2s. So each of those repeated factors are going to need a linear polynomial, like in this case, what's cx plus d above. So for x squared plus 9, you're going to need a cx plus d above. And then for the repeated factor, x squared plus 9 quantity squared in the denominator, you're going to need, I think it would be an ex plus f at that point. It's going to be a lot of coefficients. My gosh, I would hate to solve this out. Fortunately, we don't have to solve this out. We just have to give the form. It says, like, as in this example. If you click that example, I suspect it's got just the letters A, B, and C included, because this would be a beast otherwise. Right, okay, hey, we're going to evaluate this integral. So we're actually going to go through the whole partial fraction decomposition process here. The first factor, or the first fraction in our partial fraction decomposition, will be a over x minus 1. The second fraction in our partial fraction decomposition will be bx plus c over x squared plus 81. Unfortunately, x squared plus 81 can't factor without a 9i and a minus 9i, which would require invoking complex numbers, which we don't want to do. So yeah, what do we do to use real value things? We'll just go a over x minus 1 plus bx plus c over x squared plus 81. And to set up that, to solve, we'll work just like we have in previous examples, where we will find a common denominator with our here a's, b's, and c's, and then equate numerators. One of the challenges is going to be, we're not going to be able to really like eliminate the b and the c by plugging in 9i or minus 9i. That's just really not going to work. And so what do we do? Well, whenever we equate numerators, we're going to have an expression with a, b, and c. And what we'll do is we'll view the left-hand side here as a polynomial with like 82 as its constant coefficient, a 0x as its degree 1 coefficient, a 0x squared as its degree 2 coefficient. And if you compare the coefficients of equal degree on both sides, you can ultimately set yourself a system of equations. There will be 3 equations with 3 unknowns, and you'll have to go back to high school algebra 2 to solve. So this one likely walks you through the steps. These tutorial exercises are good at that. As far as this last example goes, hey, we've got a degree 2 irreducible downstairs, x squared plus 1, but it's squared. So there's going to be two factors in this decomposition, one factor over x squared plus 1 and another factor over x squared plus 1 squared. If that squared downstairs was a cube, you'd have three factors, one for x squared plus 1, x squared plus 1 squared, and then that factor cubed would be in the denominator of the third. But since we only have two factors downstairs, we'll have an ax plus b over x squared plus 1. Because x squared plus 1 is degree 2, you've got to have, you have the possibility of having a degree 1 thing above it and still being a partial fraction. So, right, the first factor is x squared plus 1 downstairs and ax plus b upstairs. The second factor is x squared plus 1 quantity squared downstairs and cx plus d upstairs. What do we do then? We write a common denominator with our expression including a, b, c, and d, and then we equate the numerators. When we equate the numerators, we're going to take the expression in the numerator to the right, and we're going to collect all the degree 0 terms, all the degree 1 terms, all the degree 2 terms, all the degree 3 terms, and we're going to compare to the left-hand side. So the constant term would equal 8, the degree 1 term would equal 5, the degree 2 term would equal 8, the degree 3 term would equal 0, based upon the numerator of our polynomial within our original fraction. And from there, you will get 4 equations with 4 unknowns. Fortunately, one of those is equal to 0, and I suspect that one's going to be the easiest one to solve. But it's going to take a lot of algebra to hammer out the details. But trust yourself and your algebra skills from your past mathematical experiences. And ultimately, when you find the A, B, C, and the D, then you will have those individual terms to evaluate. Now, when you have the ax plus b over x squared plus 1, you're going to break that down into really two subfractions, one of them being the ax over x squared plus 1. You'll use u sub on that. And then the other being the b over x squared plus 1. You'll use inverse trig for that derivative, or antiderivative, excuse me. And then when you have the cx plus d over x squared plus 1, the cx, or excuse me, x squared plus 1 squared, the cx over x squared plus 1 squared is its own factor. You can do that one by u sub, and then the d over x squared plus 1 squared. Right, goodness, how is that even going to work? Boy, I'd have to really think about that one for a second. Well, hopefully now it's not too complicated. I'm hoping that d term doesn't even show up. But, well, regardless, this is sort of the nature of the game. This one only has 4 exercises, but these exercises are a little bit more beastly. So take your time with the algebra, work through the details carefully. Once you get your A's, B's, C's, and D's, follow the integration tactics that are associated with each of those factors, and life will be good. So we'll call that a discussion here for the section 7.4, and yeah, hopefully this can be